Welcome to another session in remote sensing and GIS. My name is Dr. Raviraja. In this session, we will start the second unit, which is having remote sensing platforms and sensors in satellite system parameters. In satellite system parameters, there are instrumental parameters and viewing parameters like orbital parameters, and there are sensors type infrared or microwave sensors, and we also discuss about the platforms, geostationary, sun synchronous, equatorial orbits, swath weights, and also we will start the introduction to GIS, geographical information system. In that one, fundamentals and roots of GIS, GIS architecture and theoretical models of GIS. These are all the things we will discuss in this unit. Now jumping to the first part, satellite system parameters. Remote sensing systems use satellite or airborne platforms equipped with sensors to gather information about the Earth's surface using the electromagnetic radiation. We know this one from the first unit. These systems vary by orbit type, altitude, sensor design, and nature of the data they collect. For example, there are different natures of data. One is the optical, thermal, and microwave. So the satellite systems are categorized by two major sets of parameters. One is the instrumental parameters, another one is the viewing parameters. The principal instrumental parameters, namely wavelength, frequency, polarization, sensitivity, and these are the major principal instrumental parameters. And the principal viewing parameters are determined by the both the instrument design and orbital parameters of the satellite. These are revisit intervals, resolution, swath weight, illumination, and our observation angle and mission lifetime are the important viewing parameters of any satellite. Now, the first one is the instrumental parameters. All of the remote sensing systems make use of remote information carried by the electromagnetic radiation, of which there is an infinite range of possible frequencies. So, determined by the design of the transmitter, receiver, detectors and optics, wavelength or frequency and visible or infrared waves or microwaves, these are the types of different wavelengths we use under this instrumental parameters. So, most systems operate in specific windows. For example, visible and infrared in 0.4 to 1.15 micrometers for optical imaging. Similarly, microwave for 1 millimeter to 1 meter or 300 to 0.3 gigahertz for radar or passive microwave sensing. And the polarization is especially in microwave systems, which helps distinguish between surface types. And radiometric sensitivity measures the system's ability to detect the subtle energy differences. The higher sensitivity means lower and minimum detectable signal. So, limited by the data digitization and bandwidth, the radiometric sensitivity is a very important parameter. And the final one is the emissivity. Unique to each material, affects thermal infrared sensing. Passive microwave radiometry relies on detecting black body radiation from the objects, typically around 10 micrometer wavelength. So, this temperature and emissivity are important parameters in this instrumental parameters. Emissivity is, as I said, emissivity is a unique characteristic of the target material and its state or condition. Next, the other main use of this microwave region is for active remote sensing, by which the radiation is emitted by the remote sensing instrument and detected after its reflection from the target material. The active remote sensing in the microwave region is called radar, and main observable parameter are the range to the target from time delay to the return signal, and the reflectivity of the material, which in turn is determined by the many of its physical properties. Similarly, the sensitivity of remote sensing system measures the response produced by the radiation of a given intensity and wavelength. So, the other things being equal, it should be as large as possible, but because the output data are usually digitized, they can only span a finite range of values, so that a high sensitivity, that means low value of minimum detectable signal, implies low value for maximum signal that can be detected. So, the next one is the viewing parameters or orbital parameters. Influenced by the both sensor design and satellite orbit, the following parameters are considered as important, or they are considered as viewing parameters. One is the revisit interval, which is the frequency of return to the same area. So, the satellite will come to the same area within a span of time. It may be 1 hour, it may be 2 hours, it may be 10 hours, it may be a day, depending on the position and height or altitude of the satellite. Second one is the swath width, which is the width of Earth's surface imaged in one pass. So, that means in one pass how much area on Earth's surface it can capture. Third one is the resolution. Resolution includes a spatial, spectral and radiometric or temporal resolutions. So, I will define one by one in the next slides. These are the various types of resolution which are considered important and meaningful in remote sensing. Illumination and observation angles, for example, here nadir direction and off nadir direction are the two observation angles. One nadir is the 0 degree direction, which reduces the distortion, and similarly half nadir helps the measure the properties like reflectivity or emissivity. And the another parameter, orbital parameter, is mission lifetime. Typically, a satellite is having a 5 to 10 years of mission lifetime, in which the satellite is effectively operates with limited by the health of satellite is limited by the equipment durability and orbit decay. Orbit decay. So, next one is the orbit type. Geostationary orbits are greater than 36,000 kilometers altitude, constant view over one region. For example, polar orbit is having, they are near orbit, which often sun synchronous, good for repetitive coverage of consistent lightning. So, these are the different types of orbits and satellite parameters which can be used are helpful in determining the viewing parameters. So, for example, here as mentioned, the factors which limit the operational lifetime of satellite remote sensing mission are the robustness of the equipment carried by the satellite and decay of the orbit through atmospheric friction. It is not yet roughly possible to service satellites in orbit. So, once a piece of equipment fails, the corresponding data are forever more degraded or unavailable. The space environment is fairly harsh, and lifetime of a few years are typical for a satellite. In an orbit at a height of 500 kilometers or more, the decay of the orbit itself is negligibly slow, but at a height say 200 kilometers, the orbit of lifetime can be as short as 1 month, and this becomes the dominant factor in maintaining the satellites. The second one is the sensor parameters. Sensors are devices used for making observations. These consistent mechanisms usually sophisticated lenses with filter coatings, like for example, in simple say we can window filters, for example band pass filters or low pass filters, high pass filter. These type of filter coatings are placed on lens to focus on the area or observed on a plane in which the detectors are placed. These detectors are sensitive to a particular region in which the sensor is designed to operate and produce outputs which are representative of the observed area. For example, there are many optical infrared sensors used for detecting or imaging these from remote sensing data. For example, spatial resolution, spectral resolution, radiometric resolution. These three types of resolutions vary from sensor to sensor. Spatial resolution is an ability to distinguish small features determined by the IFOV. IFOV is the instantaneous field of view of a sensor. So, for example, in this figure, IFOV is shown as this one. the footprint of the satellite. For greater clarity of spatial resolution of any remote sensing imagery, it is more appropriate to introduce the term pixel or picture element. So, one pixel on the digital satellite imagery represents an IFOV on the ground. Each IFOV is filled by digital number, that means on off. Each digital number indicates the some inherent property of the terrain element. So, IFOV is nothing but a digital element. Coming back to the slide, this IFOV defined as the area on the ground that is viewed by an instrument from a given altitude at any given instant of time. This spatial resolution is usually determined by the instrumental parameters and by the height of the satellite above the ground. The resolution of a satellite cannot be greater than approximately Hi by d. This is the diffraction limit where H is the height, I is the wavelength, and d is the diameter of the objective lens or objective bearer of the antenna. This limit is typically of the order of 10 to 100 meters for visible band and IR systems operating from satellites in low orbit, and typically 1 to 10 kilometers when satellite is a geostationary satellite. As I said previously, there are different types of resolutions are there. One is the spatial resolution, spectral resolution, radiometric resolution. So, in this one, spatial resolution is the ability to distinguish small features determined by the IFOV. Spectral resolution is the number and width of the spectral bands. Radiometric resolution is the number of digital levels, that is 8-bit data or 16-bit data. If it is 8-bit data, the number of levels will be 256. If it is a 16-bit data, the total number of digital levels will be 2 power 16. So, for example, here the figure shows the polygon data and it shows the different types of resolutions. One is the first image is the 5-meter resolution, second is the 10-meter resolution, third is the 30-meter resolution. Here the arrow mark shows the smaller cell size means higher resolution, larger cell size means lower resolution. That means an image is having 30-meter resolution means which is having low quality, an image which is having 5-meter resolution is higher quality image. So, this is the practical image example. First one is the 1-meter data, the second one is the 10-meter data, third one is the 30-meter data. This data is taken from the National Remote Sensing Center, which is from the satellite resource sat, which is having 5-meter resolution data. 5-meter resolution data which is usually provide 5-meter data resolution, but when combined with the Cartosat data, we can scale down to 1-meter resolution and we can scale up to 10-meter, 30-meter like that also. So, in this the red color represents the trees. So, here we should know the trees may be in red color because of the arrangement of the bands. So, here in this one another image is placed in front, later blue, green, red are placed. That is why the color is shown like this. This color coding is called pseudo random color coding. So, to highlight specific regions, the geologist or any researcher, they convert into they change the arrangement of bands so that they will get the images in different format or colors, but the data represents the same. So, here let us consider how the radiance from a point source on the ground does not produce a single brightness point on the image, but produces an image which has intensity of a diffused circular region owing to a optical properties. So, when the data is captured by the satellite, you may not get a digital number directly, you will get a profile of the particular terrain, that is nothing but the Gaussian distribution of the circular region. So, based on that one, you need to find the point spread function so that we can find the amplitude of that particular pixel value. The spatial resolution achievable by radar systems is very dependent on the way the data from systems are processed. Such systems are often pulsed, and one important factor is the length of the emitted pulse. Another one example is the synthetic aperture radars. These are also integrate the return signal for a period of time while the radar is carried forward on its platform, and the integration of the time also influences the resolution. The spatial resolution of an image system can be measured in number of different ways. It is the size of the smallest object that can be determined by the sensor, that is the pixel value. So, height and width of the pixel simply. The greater the sensor resolution, the greater the data volume and smaller the area cover. Alternatively, spatial resolution can be said to be length and size of the area on the ground represented by the pixel on an image. So, these are the basis for the definition of spatial resolution can depend on these following four criteria. One is the geometrical properties of imaging system. The second one is the ability to distinguish between point targets. Third one is the ability to measure the periodicity of the repetitive targets. Last one is the ability to measure the spectral properties of the small targets. Second one is the spectral resolution. It is the number and width of the spectral band, we can say simply. Otherwise, it is the width of the spectral band and the number of spectral bands in which the image is taken. Narrow bandwidth in certain regions of ultraviolet spectrum allows us to discriminate between the various features more easily. So, that is nothing but example of hyperspectral imaging. So, we know in hyperspectral imaging within a near infrared band we take hundreds and thousands of narrow band data, so that we can distinguish various features more easily. Consequently, we need to have more number of spectral bands, each having a narrow bandwidth, and these bands should together cover the entire spectral range of interest. The digital images collected by satellite sensors, except micro sensing systems like CSAT, SIRB, RadarSat, these are some Indian satellites, have been multi-band or multispectral individual image separately recorded in discrete spectral bands. For example, multispectral image refers to the viewing of a given area in several narrow bands to obtain better identification classification of the objects. Here, the viewing of a given area means viewing of a same spot with respect to the several narrow bands, so that the space in this for the same spot you will get multiple spectral images. Here, this is the data taken from website NRSC. Here, first one shows the panchromatic data, which is having a band 8 of Landsat 80 shows data. Another one is the multispectral data, which is having 3, 4, 5 bands, and Landsat 8 data. I'm sorry, this data is taken from Landsat website. The multi-stage imaging refers to the observations of the same area from different positions of the platform, which is called stereographic data. That means one is taken from some particular angle, another image is taken from particular angle. By this way you can get the height of the objects and another profile of the area. Multi-stage imaging refers to the observations made over the same area on different dates to monitor the objects like crop growth. This is also called temporal resolution. So, we get the previous date data and the current data. By using both the data, we can estimate the growth of the crops. The term spectral resolution refers to the width of the spectral band. Spectral resolution can be explained by the considering 2 points. One is the position of the spectrum, width and number of the spectral band. They will determine the degree to which individual targets can be determined on the multispectral image, and the use of spectral imagery can lead to a higher degree of discriminating power than any single band taken on its own. So, this is a concept of spectral resolution. Here it is showing two different reflectance curves by use for one is for unhealthy vegetation, another one is the healthy vegetation. So, in this way we can also find the different types of healthy vegetation and unhealthy vegetations. So, that means various surface features can be identified by taking these multispectral bands. For example, differences in spectral reflectance of Whereas rock types are separable only if the recorded device is capable of detecting the spectral reflectance of the target in a narrow spectral wave band. So that is why hyperspectral imaging is the most popular thing. In the as shown in the figure, it can be seen how healthy vegetation can be discriminated from unhealthy vegetation. Most of the difference occurs in infrared region only. Since we discussed earlier, the infrared regions are more responsive to the vegetation regions. Unfortunately, it is not possible to increase the spectral resolution of a sensor simply to suit user needs because of the signal to noise ratio, which is defined as the ratio of the total radiant energy to the noise equivalent power. And also by increasing the number of bands, the cost of launching the satellites will also increase. Maintaining satellites with these many number of bands is also difficult. Multispectral scanning systems are designed to sense energy over small IFOV and in narrow wavelength bands. Similarly, since IFOV are very small, the amount of energy incident on each of the system detectors is very low. If IFOV is not very small, the clarity of the image will go very bad. So, for example, that is why 1 meter resolution is looking very good when compared to the 30 meter resolution. Hence, the detectors must be very sensitive to output a signal and stronger than the level of noise. The noise is an extraneous and unwanted response which shows a signal from detector as it would appear in the absence of system noise. Similarly, we can define the radiometric resolution. It is the capability to differentiate the spectral reflectance I emittance between the various targets. So, this depends on the number of quantization levels within the spectral bands. In other words, the number of bits of digital data in the spectral band simply. So, for example, as I show in the figures, the first image is having only two levels. That means it is having only 0 and 1. 0 represents black and 1 represents white. So, similarly, if I increase the radiometric resolutions to 4, that means the image is having 4 colors 0, 1, 0, 1, 1, 0. So, that is 0, 0, 0, 1, 1, 0, 1, 1, 4 levels. So, it is we can identify more number of variations when compared to the 2 level image. Similarly, if I increase to 8 levels, that means 2 power 8, I have 256 different shades of gray levels. Okay, so it is obviously more higher quality when compared to the previous 2 level or 4 level images. If I use 16 levels, that means 2 power 16, which is approximately 65,536 number of gray levels, which surely provides more number of data when compared to the previous levels. So, there are similarly there are different types of imaging systems are there. Sensors, for instance, sensor systems, first one is the as we discussed, multi-spectral sensing systems, thermal sensing systems, microwave and radar sensing systems. So, the multispectral systems or multi-band image systems may use conventional type of cameras or combination of them along with filters for the various bands. In the visible part in the scanning system, multi-band imaging. This way, electromagnetic energy can be recorded by scanning the ground a bit by bit. And second one is the thermal systems, which uses the radiometers or photometers or spectrometers or thermistors to detect the temperature changes. And the final one is the microwave sensing or systems. They use the antenna arrays for collecting and detecting the energy from the terrain elements. So, in the next class, we start with the imaging sensor systems with the multispectral imaging systems. Thank you.